If we want to extend the capabilities of our Haskell programs a little bit further than some of the built-in types will allow us, we can actually define new data types. These data types can also extend, or the word is derive, from existing data types to get some of those features that those existing data type categories have. There are a few different options for how we define our data types. One way is to give a limited number of named values. For instance, if we were looking for only a certain set of country names, then we could name each of those countries in our type name, and our type name might be country, for instance. And then we can state what other existing types they are deriving from, and we'll see some examples of that. And then another way that we can define our data types is to define a constructor that takes some sort of inputs to it that will be other types. And that allows us to create many different values that don't automatically have names in the type. We may store them as variables with names, but they don't automatically get names like, China or United States or things like that the values would have in our first example. We can, however, mix and match these two. If, for instance, we had some predefined named ones that we knew we wanted to make sure got included, we could include those. And then we could just put a bar and some constructor types that would allow us to build, a larger number, probably unlimited number of possible types using ints or strings or whatever as the inputs to those. And we'll see examples that are purely one of these or purely the other, and some examples that do mix and match the two of them. So here's one example that uses only named types. It's the direction type that I've defined here that has only north, west, south, and east. The ordering of these mattered in the example I'm doing here. It won't always matter what the ordering is, but in this case, the ordering does matter because I've derived from the Enum type. That's a type that allows us to enumerate between the values, like how we can enumerate between integers or things like that. I've also derived from the show type, which will automatically allow them to be shown according to the names that were given here or according to how they were constructed if we use the constructor types, which this one doesn't have. I've then defined a few functions for them. So you can see that turn left of most values can just ask for the successor of that value. So for north, the successor would be west. For east, however, there is not a successor. An enum does not loop back, just like the integers don't loop back to 1 typically. They keep going, and in this case, these aren't infinite. They're a finite set, so they have a limited last value. So if I want people to be able to turn while they're facing east, and I want them to be able to turn left, then I need to manually write a case for east. And we can do this based on our type names there. And Haskell will infer that the turn left function is referring to a direction because of the fact that I'm using east and north in it there. So turn left on north will give me west. If I turn left, turn left, turn left on east, well, we know that the first turn left will give me north, then west, then south. And so south will be my result. You see I've defined turn around as turning right twice, and that turning right needs a special case to go from north back to east. So these are just a few relatively simple functions that I can use for these directions. You can see that because I derived from show, it will show me the types. If I don't derive show and I try to display a result, then I'm going to get errors that there's no way to show those results of that type. Another interesting thing that I can do, because this is an enum type, is I can do those ranged lists where I create a list from north to south, and it will go northwest, south. I can create a list from north to unlimited, but it will be limited because enums are typically limited. If I wanted one that went further, then I might have to do some tricks with my turn left or turn right to be able to get more than just those. If I wanted to take 8 turns, then maybe I could map that turn left 8 times or something like that. I can map onto lists of that type as well. So I map turn around onto it, and you see that I get the opposite of each of the directions that was given there. Here is a data type called RGB color that is a constructed type. It has no named versions when the type is declared. It just declares that an RGB color can be constructed from 3 ints, a red, a green, and a blue value, presumably. And then down below that, I have manually defined a few types. A pure red is RGB color of 25500. Then I've defined a pure green and a pure blue. I've defined some functions that work with the RGB color type. So here's add color. It takes an RGB color and it pulls out the red, green, and blue from it. And then another RGB color pulls out its red, green, and blue. And then it adds the reds, adds the greens, and adds the blues. You'll notice I've done nothing to guard to make sure that these don't go above 255. That would be added functionality that I might want to put onto this as well. But I didn't do it here. So here I've added, here I've manually defined purple to have full red and full blue. But I can also define purple by adding the colors red and blue. And you can see that purple is equivalent to the add color red and blue. Okay, and then I did not, in this case, derive from show. And the reason I didn't derive from show is because I wanted to manually define how these would be shown. If I didn't manually define how they would be shown, it would simply say RGB color and then the 3 numbers, no parentheses or anything, just one statement. So RGB color 25500, for instance. And I wanted to show a little bit more about it. I wanted to put it in parentheses and some commas, and I wanted to have just color. I don't want my users to have to worry about that it's an RGB color type. So what I do is, instead of deriving show and getting that automatic behavior, is I create an instance of show RGB color where the show function for an RGB color breaks out the R, G, and B values. It puts on the word color, a colon, and a space, and attaches that to the string representation of the tuple RGB. And so that gives us results like the ones that are shown here. And I could do more things to kind of refine how it was shown in some particular way. There is a built-in type that gives us some good illustration of type features as well. I'll give you an example of how it could be defined, and this is probably roughly how it's defined in Haskell, but it is a built-in type. You don't have to define the maybe type. In fact, some functions that are built in Haskell already return maybe types, like the data.lists find function, because it may not find the thing. So the built-in maybe type allows for handling when no value is able to be given, such as a search that doesn't find a result. It has one named value called nothing, and then one constructor called just. And you'll see that maybe needs a type that it's going to be storing when there is a result. When there is no result, it's just nothing. But then when there is a result, we have a just that has some value. This makes the language a little difficult around this, but it allows us to do things like if we really didn't have a reasonable result to return. Say returning a -1 wouldn't make sense, and returning, an actual number wouldn't make sense. Well, we can return nothing. So I've written a divide function that takes an x and a y. If y is 0, well, I don't want to just let it try to divide by 0. I want to give nothing. Now the trick to this is that means I'm not returning a number. I'm returning just and then the number, which I can't do divide with, for instance. Divide takes two regular numbers, so I'll have to pull out the 2.0 from that if I want to actually do more math with it. This can make things a little complicated, and that's why this is not as straightforward as how in many languages you can return null, and it's sort of treated like any type. Well, here it actually has to specifically be the maybe type. So the find function in data.list can take some criteria and see if there's anything in the list that matches that criteria and return you the first thing in the list that matches it. So if I look for something that's equal to 3 in the list 1, 2, 3, it will return me just 3. If I look for something that's equal to 3 in the list 5, 6, 7, it will return me nothing. Here is, I've set the multi-line so that I can show you a multi-line function in this example. And I want to remind you that that's there so that you can use it when it's necessary for you. So then I've defined getVal if there's a nothing to give me 0, for instance. And I've defined getVal when it's just a value to give me out the value from it. Now, you want to be careful in using something like this because what you provide as your nothing could cause problems if it could have been one of your real values. So you want to be very, very careful in trying to pull out the something from the just if your nothing value really can't make sense. And so these maybe types can be pretty complicated for beginning Haskell programmers to work with because of that fact that you can't just say, find the thing in the list and then add it to 12, for instance, because you can't add 12 to a maybe. You can add 12 to a number. Here's another type that we're defining that will allow us to define expressions. And this is a pretty simple set of expressions, but we could define a more complicated set of possibilities for expressions. We've got literals that are integers in my expression setup here. And then I've defined addition and subtraction for them. So a literal is a constructed type that takes an integer. An add is a constructed type that takes two expressions. And a subtract, is a constructed type that also takes two expressions. So you'll notice that the type is used inside of itself here, that we're able to say we can make expressions of expressions. That allows us to do things where we could add the results of two different expressions, for instance, and we'll do that down below. So here is a function that allows us to evaluate expressions. It takes an expression and gives us an integer as a result. Eval on a literal will just give us the value, the integer value from that literal. Eval on an add will take the two expressions that the add has as parameters and call eval on each of them, summing their result. You can imagine that this might lead to more eval calls and more eval calls and more eval calls if each of those expressions was complex as well. And sub does the same thing, taking the two expressions, evaluating each of those expressions, and doing subtraction on the result. So here's some examples. Calling eval on the literal 4 gives us 4 out. Calling eval on sub with the literal 3 and the literal 2 gives us a result of 1. Eval on sub where one side of it is an add expression and the other side of it is just the literal 2 as an expression. So here we are adding 4 and 1. That will get evaluated to 5, and then we'll get to subtract away the 2 in that literal over there and get the result 3. Here, I'm mapping the anonymous function that takes an x from my list and does sub of a literal with that x and a literal that's 1. Now, this is a pretty complicated way to do subtraction, just -1 on each item from the list, but you can see that it provides us a tool for building these sorts of expressions. And so we can build complex things even using pretty simple and small types like this, where we could define our own sort of little sub-language in Haskell. And Haskell has been used to construct scripting languages and other sort of linguistic things. And so this kind of structure is not that unrealistic in Haskell in real applications. Here I'm folding where I eval adding x and y, and those x and y are just summing my list that I was given here. So this is equivalent to folding plus over that list. But again, I'm using this new type that I've built that uses expressions in this constructed format here. So that's kind of neat to be able to build sort of our own language inside the language by building what expressions can look like. We also can define full-fledged data structures using these data types in Haskell. So here I've defined a module for linked list, where the linked list type takes some input type, A. This is like a generic parameter in Java or a template in C++. So it takes that A, and so a linked list of A's will look like this. Either it will be null, which is the empty list, or it will be a node of A that points to a linked list of A. So you can look at this parenthetical part here as being like the next pointer in a C++ or a Java style linked list. So the next pointer is just defined by saying that a node can have a linked list as its next, and in fact must have a linked list as its next. Now, that linked list that it has as its next may be null, and eventually should be null for our lists to be constructed. I've derived from show, so you'll be able to see the linked lists, but you'll see that it's in this sort of default format. So the head of a linked list, well, head, if there's a node, we get its x and we return that x. Tail, if there's a node, we ignore its value and we take that parenthetical linked list part, which we've called t here because it is the tail, and we just return that t. So here we can see some examples here. L is defined here as node with 1 as its value, and then it has a next, which is a node with 2 as its value, and that node's next is just null. So this is essentially a 2-node linked list that ends with that null there. If I ask for the head of it, I get 1 because that's the value of the first node in the linked list. If I ask for the tail, I get the node that has 2 as its value and null as its linked list next. Here, if I ask for the tail of L, well, the tail of null, that is null. If I ask for the head or the tail of null in the way I've constructed these, I left a non-exhaustive pattern in there. So it will cause some errors if you ask for the head of null, but this isn't that unreasonable because the same is often true in the case of asking for the head from an empty linked list in other languages too. What kind of error you want to indicate and how you want to do it could vary. We could, for instance, have defined one where it said head of null is equal to nothing and this is equal to just x, and we could have used the maybe type for it. But as we saw before, those can get complicated. So here I've just allowed it to cause an error. Maybe not the most helpful error in this case, and there's definitely room to improve on this module. So, however, I've also given some nice ways to construct and to get the values from the linked list. So we can go from a list to a linked list recursively here. If we have a list that's empty, well, our linked list is null. And if we have a list that has some head and some tail, well, we make a node of x, and then its next will be the result of from list on the tail. And so this will keep calling recursively until it hits a null or an empty list as the tail, which will give us null as the last next in our list. And we see that here. Let L equal from list 3184. Well, it constructs a node with 3. And then for its next, it constructs a node with 1. And for its next, it constructs a node with 8 and a node with 4. And then finally, the tail would have been the empty list. And so its next after the 4 is null. If I ask to go to list, well, that will walk through until it's a null. When it's a null, it gives an empty list. But when it's not null, it gives the value A combined with the result of calling toList on the tail. And so, again, we're recursively defining this data structure, as you can see in the way that it's shown here, and we're recursively being able to build and pull apart the pieces from it. An add at the head is actually really easy. If we want to add head of x to some existing linked list y, then we create a node xy. I probably could have named this L or something to make it a little clearer here. This part is an existing linked list. I want to add x as the head. And so I just return a node that has x as its value and the existing list as its next. Now, bear in mind, keeping that functional mindset, this does not change the existing list. This returns me a new list. And so we have to be careful that if we're trying to add head, we're actually doing something with the result of that, not assuming that that changed the list that exists here. Add tail is a little more complex because if you're adding at the tail, you have to actually get to the tail. If it's a null list, well, that's easy because I can construct a node with x as its value and null as its tail, and now we have a list. So what I do up to there is I recursively call with x and node and a node that has some a and then some t tail. I reconstruct the node to have node with a as its value, and its tail will now be whatever the result is of add tail with x and the existing tail. So what this will do for most nodes is nothing at all. It'll just reconstruct that node and it will eventually get the next that it had. But for the node that had null as its next, then it will get a new node as its next that is the node with x as its value and null as that one's next. So it extends my list by one more. And again, bear in mind, it does not change this original list. It returns me a whole new list that has that one value added. Now, there are intelligent ways that these are handled in the background in Haskell so that you are hopefully not always creating huge whole new lists, but are reusing some existing stuff that's stored in memory. But don't think of it as changing the original list because it will not. It will give you a new version of the list that has that extra value added on. And here, just to show how we would sort of step through the list and find something, is a max function for this type of list. If you have a node that's only x and null, it gives you x because the singleton list always has x as its max. Otherwise, if it has x and some tail, well, it's going to look for the max of that tail, and it's going to either return you x if x was larger than that max of the tail, or it's going to return you y if x was not larger than the max of that tail. So it's recursively calling this max function until it reaches the tail, gets a max for the tail, and then is able to compare coming backwards. Not tail recursive, but will nicely find the max for any non-empty list. For an empty list, it would error just like my one above. You can decide how you would want to handle that in practice. All right. And if you thought that that wasn't a big enough type of data structure to be able to define in a functional language, well, let's try trees. We can even define trees in Haskell using these new data types as we define them. We can define a tree of A's to either be empty, and that's a special type that's named here. So we would want to be careful that empty wasn't a name that was already taken, or we might want to use some longer name like empty tree, some people will use, or stuff like that. But empty is going to be one of the named types for our tree. So that's an empty tree. Or it will have a tree node with A as its value and a tree of A's and another tree of A's. These will be functionally the left and the right. Remember that A is not an actual variable name. A is a type name here. So we have a node of A and a tree node of, and a tree of A's and a tree of A's. These are subtrees. Left subtree, right subtree. And it gets a little nasty when we have to write them out. So for instance, if I take just the tree that has a single item in it, we have to define a tree node with that single that single value, and then it has two other other trees that are empty and empty. Those are its left and its right. And so we might eventually want to write some nicer ways to display this tree, but for now we see that's a node that has a value and no left and no right. So it's a single value tree. We can ask the size of that tree. I've defined a size. If it's empty, it's 0. Otherwise, we do 1 plus the size of the left and the size of the right, where L and R are those second trees, the first and second trees that are defined inside of the node. So in the case of this one, it would have accumulated the 1, and then it would call the size on one of the empties and size on the other empty, getting 0 and 0. And so its result for size would be 1. Okay, and root just gives us the value of the current node, and left gives us the left subtree, and right gives us the right subtree, or the first subtree and the second subtree here. We can test, or we can do things like put it to a list in pre-order, or get it from a list as pre-order. And so to do these, it's not too dissimilar from what we did for the linked list. We will, for an empty list, give an empty tree. Otherwise, for an empty tree, we will give an empty list for giving a pre-order list version of this. Otherwise, if we have a tree node, we'll use its value x. Remember, pre-order is this node, then the left subtree, then the right subtree. Well, that's easy. We have x combined with the result of calling pre-order on the left subtree, merged with the result of calling pre-order on the right subtree. And so for my singleton tree here, that would get called once. It would construct x, and then it would end up combining x with the empty list merged with the empty list. So it would be x combined with the empty list, and we would just have that 1 inside of a list. I've done the opposite direction, getting from a list into a tree. Well, give me an empty list, and I'll give you an empty tree. That's simple. If it's a list that has a head and a tail, then I will get the middle value of that so that I can pull out what should be the left subtree and the right subtree by taking the length of the tree and dividing by 2. And then I take up to the middle and I drop after the middle. I take up to the middle and I drop what comes before the middle. And then I'm able to create a tree node on x, the current value, and the left subtree that was created by recursively calling on part of the list, and the right subtree that was created by recursively calling on the other part of the list. I get the benefit also that this will be balanced and insofar as the list is divisible by 2. And so I can see that I'm able to do that with the list 1, 2, 3. It creates me a tree node with 1, and then the left subtree of that is a tree node with 2 and empty children, empty subtrees, and then the right subtree is a tree node with 3 and empty left and right subtrees. The size of this will be 3 because we get 1 for the middle, and then we recursively call on the others to get 1. If we ask to put it into a pre-order list, then we will get out 1, 2, 3 again, because 1 was my root and 2 and 3 were its children. Bear in mind, this is not any special kind of tree other than a binary search tree. You could, however, write code in Haskell to generate, for instance, a binary search tree or other types of data structures that you wanted to, all by being able to define maybe some named types and some constructed types, especially when those constructed types can be recursive and hold on to more and more of the values of the types that you're wanting to store in your data type. And so you can see that constructing new types in Haskell has a pretty wide range. We can define some really simple ones that only have a few named values. We can even define ones that are constructible with just some of the primitive values like ints or strings. And we can define these complex, recursively defined types that allow us to build full-featured, potentially, if you want to put the work into it, data structures within the language. And they're still following that Haskell and that functional mentality and style of being recursively defined and being immutable. When I add something to them, I'm generating a new linked list or tree or whatever the data structure is, and still having that original kept as it was to be able to do whatever I need to with that newly derived type, and possibly still revert back to the original if I return from a recursive call, for instance, or things like that. And so you'll get some experience with doing a range of different possible uses of these user-defined types in Haskell.